Hello friends, welcome back my YouTube channel MS Maths. In this video, we are going to discuss about measurable functions. In the previous video that we have discussed what is the sigma algebra of these sets and what is the concept of the measurable set and what is the Lebesgue measure that we have discussed in the very previous videos. Now we'll discuss the measurable function and further we'll discuss the theorems on the measurable functions and the property of the measurable functions. Then so many things we'll discuss in this previous and the next videos. So subscribe my channel, share my channel, and press the bell icon, hit the like button. So let's start the topic that basically the measurable functions. What is a measurable function? If it is if E be a measurable set, it means it is a the outer measure and the inner measure are equal for this case, and the same thing that E be a measurable set. It means there is a function from E to R star where R star is nothing but the real number together with the set minus infinity to infinity. It means whole terms will be there where f is a mapping be an extended real valued, not external real valued. It is basically the extended real valued function b point, or it is a function b point on a measurable set E. Then f is said to be measurable function if for each alpha belongs to real number is basically if it will satisfy this property, then we'll call it the measurable function. Okay, so what is the property that we have is basically this function is called x such that f of x greater than of alpha is measurable. If this set is measurable, then we'll call it is a measurable function. It means it is a measurable function from f is basically from E to real number. Now we have a theorem on the based on the result of this, then we'll prove it. What is the measurable function we'll get in this theorem. So the theorem is just like there are four results. We'll prove one by one all the results. So what is the statement of the theorem is basically the let f be an extended real valued function. It means it is from E to R star, and R star is basically R union of minus infinity to infinity is called the R star. Okay, extended real number set, you can say. Okay, so whose domain, the function whose domain is a measurable set, then the following measurable set, then the following conditions are equivalent. These all conditions are equivalent. What are the conditions? For each alpha belonging from real number is basically the x such that f of x is greater than alpha is measurable, f of x is greater than equal alpha is measurable, f of x is less than alpha is measurable, and f of x is less than equal alpha is measurable. These all conditions are equivalent for this case. So we'll start the proof from here. So what is the proof for this? Let's start. Let D be the domain of the function. D be the domain of the function f, which is from E to R. Then D be also measurable set. If your function is measurable, then it is a measurable set. So for prove the equivalency result, or if we wish to prove the equivalency for any theorem, then we'll start with the result we'll take as like one result will take as a given and another result will prove. It means we'll start with one implies that second. It means the given is for 1. So the given part is for this is basically the result 1, and to show part is basically the second. Okay, we'll start with this. So what is the first part is basically they consider x such that f of x is greater than alpha. Well, I think it is greater than alpha. I think there should be greater than alpha. Yes, and it is equals to the intersection n is equals to 1 to infinite x such that f of x is greater than alpha minus 1 by n. If f of x is greater than alpha, if I will remove some quantity from alpha, still or remain f of x is greater than alpha minus 1 by n and intersection. So the intersection for this. So by the result one, oh yeah, it is equal. Yeah, consider this is what this is what equals to this. Now by the result one, the set what x such that f of x is strictly greater than alpha for each n belonging from the real natural number and alpha belonging from the real number, also countable intersection countable intersection countable intersection of measurable set is also, and basically, yeah, the countable intersection of measurable set is also measurable. Hence the intersection n is equals to 1 to infinite is what x such that f of x alpha, yeah, is greater than alpha minus 1 by n for every n belongs to n is measurable. This set is what is measurable. Okay, if it is measurable, then it is equivalent to what? This. Then x such that f of x is greater than equal is measurable. It means in the first step of the theorem, we have taken first as a given or result, and then we showed that second. In the second, we'll take second as given and we'll show third. In the third step, we'll take third as result and we'll show fourth, and fourth as result will show first. So all the four properties will be equivalent in this case. Now we'll take second as a result and we'll show third. So for each alpha belongs to real number x such that f of x less than alpha is basically what? Domain minus x such that f of x greater than equal alpha. Since D be a measurable set and x such that f of x greater than equal is measurable by previous, and hence the difference of to measurable set is also measurable, then the set x such that f of x less than alpha is what? Measurable. We have proved from second to third. Now we'll take third as result, we'll prove fourth. Okay, what we have? X such that f of x less than equal alpha is what? Fourth result. It is basically the union n is equals to 1 to infinite is basically the x such that f of x less than alpha plus 1 by n. Then what? The countable union of a measurable set is measurable. Then x such that f of x less than equal is also be a measurable set. Next, we'll prove from fourth to first. The same thing, it will be domain minus. So it is what? X such that f of x is greater than alpha is basically the d minus x such that f of x less than equal alpha. Then if d is a measurable set and from previous x such that f of x less than alpha is also measurable set, then the difference of measurable set is also measurable, then x such that f of x greater than alpha is measurable. So this is the result that we have proved here. So this is what the theorem on the measurable function and the concept of measurable function. So thanks for watching my video. Keep watching MSMaths. Thank you. Bye bye.